Here's problem 7.06. It is a boxcar problem. We got a boxcar of known mass, 8,000 kilograms, and a boxcar of unknown mass, whatever. This boxcar comes in, it hits this one, it sticks to the other one, and they move off with a final velocity of 5 meters per second. Question is, what's that mass? So, looking at this problem, all the things that we do, we hardly ever talk about two objects that hit each other. Whenever we do talk about two objects that hit each other and interact, that is probably going to be a momentum problem. Okay? If they hit and stick, if they hit and bounce off, most likely a momentum problem. Here we have these two sticking off and sticking and moving off together. So this is going to be, it's most likely going to be an inelastic collision. We're going to lose some energy here. Elastic wouldn't lose any energy. And so we need to figure out what the heck is going on there. So we're using momentum. And momentum is mass times velocity. And momentum is actually a vector. It cares about direction. So looking at the problem, before anything happens, who has the momentum? Answer that. It's the thing that's moving. Now, here's the big error that I want you guys to really consider. And if you're watching this video, most likely you're not going to have a problem with this. It's the ones that don't watch these videos that really are going to have the issue, which is kind of ironic. This equation is going to represent the momentum of just one object. You're going to make the conservation of momentum equation from this, okay? So, looking at these two objects, who's moving? That one. Who has the momentum? That one. If this one's not moving, it has no momentum in this system, okay? So we're looking at something called conservation of momentum. It's very important. Although a very simple problem, it's very important that you understand what's going on. So if you're just copying this for the answer, great, awesome, thanks for watching my video. But you really actually need to know what's going on, because it's going to hurt you later on if you don't know that. But looking at this, here's the equal sign. The equal sign is going to represent something happening in physics. There's a before and there's an after the equal sign. Like chemistry, there's reaction, before and after. So here, before anything happens, we can talk about the momentum of both objects. And I'll call this object 1, I'll call this object 2. And without even putting any numbers in. Some of you guys hate it whenever you don't put numbers in. That actually makes it a lot easier to think about and a lot easier to look at. So we've got the momentum of object 1 and the momentum of object 2. Now object 2, the velocity is 0, so we can just take that out. We didn't even have to write it. I'm just writing it so you guys can see it. Okay? All the momentum in the beginning has to deal with object 1. Then we have a collision. They interact. Do they still exist on their own? The answer is yeah, they're still there. As object 1, with a mass 1, and it's going to have some velocity after this collision. We're going to represent that with a v1 prime. The other thing is going to have some momentum too. It still exists. It's v2 prime, because the original v is over here. Now we can actually plug stuff in. The mass is here, 8,000. The velocity of it is 13, and it's going to be positive 13. Momentum cares about direction. Velocity is going to make it so. If it's velocity squared, like in energy, direction doesn't matter. But here it actually does. This is going to be plus m whatever times 0, so that's going to be 0, equals m1, 8,000, v1 prime. What is v1 prime? v1 prime is 5. They stick together and they're both moving at that. So 5 plus m2, which is what we don't know, and v2 prime. v2 prime is 5. Okay, so we actually have that. Looking at all this, do I have one unknown? Yeah, it's m2 right there. And so let's just solve it, let's just take it over. And this is why I don't like to plug in numbers necessarily into more of the end. Like, do all your calculation, because look, we got 8,000 times 13 and 8,000 times 5. What's the difference? So 8,000 times 13, if I really wanted to write it out, minus 8,000 times 5 is equal to m2 times 5. And 13 minus 5. 8,000 times what? What's 13 minus 5? It's going to be 8 is equal to M2. And there's a 5 attached. So I'm just going to divide by that. Divide by 5. And that should give me my mass. So 8,000 times 8, 64 something. Yep. Divide by 5, and that gives me 12,800. 12,800 is going to be my mass for this unknown object. Rounds up to about 1,300. 13,000, sorry. Okay? So, momentum. We're making this equation based upon what things are in our problem. To move on, this next problem, 7.07, I'm pretty much doing your homework for you, so if you're watching these videos and you're really getting it easy, as far as me doing your homework for you. Other people probably just looking up the answers. They might not be getting as much out of this. They're going to be screwed on any other quizzes or tests that we take because they're just not, they're just copying down numbers. Okay. 7.07 says a child in a boat throws a package, and let's see. The mass of the child is something, the mass of the boat something else. Well, we got to find. Calculate the velocity of the boat immediately after the throw, assuming that it's initially at rest. So we have, let's draw a little picture. We've got another boat here. We've got a kid, and they're throwing a package off the boat, causing some pollution, whatever. So this thing goes, and they throw it off. Well, think about what's going to happen, first of all. Yes, it's a physics problem. Yes, there are numbers. Think about what's actually happening. If I throw this package that way, I'm the child, okay? If I throw the package to the right, you're putting a force on the package. To the right. The package is putting a force on you, pushing on it. So you're going to have a force on you to the left. So if you throw something to the right, this whole thing moves off to the left. Okay? So it says, a child in the boat throws a 5.5, mass of that is 5.5 kilograms, and they're going to throw it with a speed of 10 meters per second with relation to the still water. The mass of the child is 21.8, so this kid, 21.8 kilograms. The mass of the boat is 34 kilograms. Okay, the kid is in the boat. What kind of problem is this? This is a problem, it's not a collision. This is more like an explosion. Explosions are just collisions in reverse. Collisions are just explosions in reverse. Okay, it says calculate the velocity of the boat immediately after the something, assuming it was initially at rest. So we're looking at a momentum problem again. So here's our equal sign, just like we did before. Before the equal sign, before anything happens, before anything is thrown, before anything moves, nothing's moving. So who's got the momentum? Nobody. So for this system, before anything happens, the momentum is 0. Could the boat have been moving to the right? Yes. Could the boat have been moving to the left? Yes. In that case, both the child and the boat would have momentum, and the package. But right now, we don't have any momentum. It's nothing. Nobody's moving. After this package is thrown, who's got the momentum? Well, the package will have momentum because it's moving off to the right, and the boat and the kid will have momentum because they should be moving off to the left. And what we know is that due to conservation of momentum, P's momentum, that we should have 0 overall because we had 0 in the beginning. So looking at this, how many items do we have? We have the mass of the boat and the velocity of the boat. We've got the mass of the child and the velocity of the child, and we've got the mass of the package and the velocity of the package. Now, 2 of these things are the same. Which one are they? The velocity of the boat and the velocity of the child. The child's inside the boat. Okay? Now, don't think it's weird that I used a plus sign here, because later on we're gonna have a negative velocity for some of the things that are going to the left, so it's okay. So looking at this, we have 0 is equal to the mass of the boat, 34. We have the velocity of the boat, which I don't think we know that. Yeah, we don't know that. We're looking for that. Plus the mass of the child, 21.8. And the child's in the boat, right? So the velocity of the child's actually the same thing as the velocity of the boat. And this is after the throw, plus the mass of the package, 5.5, and that's moving at a velocity of 10 meters per second. So the mass is 5.5, velocity is 10. Well, looking on all this, let's do a little bit more math here. This is now just a math problem. Physics is done. 34 plus 21.8 gives me 55.8 velocity of the boat after the throw, plus 5.5 times 10, move it over, 55. Okay, the only way for this whole thing to equal 0 is if the velocity of the boat's negative. And didn't that go with what we said before? If we throw the package out to the right, the boat and the child should go to the left. And so to solve it, we have negative 55, move that 55 over, equals 55.8 v of boat prime. And so negative 55 divided by 55.8 gives me velocity of the boat, and that equals negative 0.986 meters per second. And double check with my answer up on Mastering Physics, and I am correct. And you should be correct. Don't screw up. There you go. 2 more problems.